Let's look at the historical development and the organization of the periodic table. Going way back to Aristotle in 300 BC, Aristotle organized the matter that he saw into four things: earth, water, air, and fire. And his ideas persisted for 2,000 years. It wasn't until the latter end of the 1700s with Antoine Lavoisier. He was the Frenchman that is the father of modern day chemistry. Along with his wife Marie, he was able to take very careful measurements and he was able to come up with the law of conservation of mass, that matter cannot be created nor destroyed. The work that he did with the elements is that he made a list of the 33 elements and then he tried to organize them and tried to classify them. And he was able to separate them into characteristics of metals and nonmetals. A few years later, a German scientist by the name of Dobereiner, he took elements that reacted like each other and he organized them in little groups that he called triads. And these are his triads put on our modern day periodic table. And we can see some of the validity of his claim that these elements should be grouped together because we see in our modern day periodic table they are grouped together. Dmitry Mendeleev in 1869, he was a Russian scientist, and he took all the known elements at the time and he put them on little cards. And then he did a card sort. And he varied the length of his rows, either 7 or 17 cards in each row, and he left blank spots. So as he was organizing this and looking for patterns, he found that there should be some elements where there were not. And so he left those blank spots. And then he published his periodic table or his organization of the elements. He challenged those who read his paper to go and find these elements. And they did. They were able to find some elements. For example, he predicted that should be an element right below aluminum that should be like aluminum but heavier and more dense. He published that in his periodic table paper, and scientists went to find it and they found it and they named it gallium. How he organized his periodic table was by the mass. So he just went by the weight of the atom. So he went across the row, getting heavier and heavier, and then when he found that the properties of the elements started to repeat, he started a new row. And so he ended up with different row lengths of 7 and 17. William Ramsay in 1894, starting with argon, which is part of the air that we're breathing, he was able to discover a whole group of gases that he called the noble gases. And the noble gases get their name from royalty. So royalty is noble, and these gases, they are noble in that they do not want to bond or react with any of the peasants, any of the other elements on the periodic table. And Ramsay's noble gases, they fit right onto Mendeleev's periodic table, just tacked in on the end. In 1913, Henry Moseley, he was a British scientist, he determined the atomic number of each element, and he did this by using something called X-ray crystallography. So he was able to look at the diffraction pattern of shooting X-rays at different samples of elements, and he was able to determine how many protons there are in each of the elements. And so he went to Mendeleev's periodic table and he just modified a few of the elements. And this is how our periodic table is arranged today. And this is the periodic law. So the periodic law says that the properties of the elements are a periodic function of their atomic numbers. So Moseley, he just modified Mendeleev's periodic table. And this is the periodic table we have today, that it is organized by number of protons. And then when we get a repeating pattern of reactivity, we start a new row and we end up with 7 rows on the periodic table. So these rows, they're also called periods. And as I said before, there are 7 periods on the periodic table. And then if you go down a column, that is called a group. And it's also called a family. Both those names, families and groups, are both appropriate to describe the columns on the periodic table. Just for convenience, we do number the columns. Going across left to right, we can number the columns 1 through 18. And another common way to number them is to use Roman numerals. So the main group elements, they start with an A. And the transition metals, or these down here in the valley, they start with a B. Sometimes you do see a Roman numeral system, and so just to go through what each of the Roman numerals mean, because I find that they have stopped teaching this in the elementary school. Roman numerals is just kind of a tally system to describe a number. So looking at numbers 1 through 10, we can write Roman numerals for those. So again, Roman numerals is just a little tally system. So if I have a 1, I just write a little tally. You can make it fancy and give it a top and a bottom, but you don't need to, but you often see it written that way. A 2 would be 2 tallies, and again, you can make it fancy. A 3 would just be 1, 2, 3. And let's get 4 for right now. Going on to 5. So a 5 would be a V. And again, you can do a top and a bottom if you so wish. Let's go back to the 4. So the 4 is listed as a 1 and then a V, meaning 5 minus 1. That gives us 4. And let's go on. So 6 would be V with a 1. 7 would be a V with a 2, 5 plus 2. 8 would be a V with 3 tallies, so 5 plus 3. And then 9, let's skip that. 10 is an X. And going back to 9, you would list that as 1x, meaning 10 minus 1 would give us 9. So we have our main group elements. They go from 1a here to 2a here. So sometimes they just write the number also. 3a, 4, 5, 6, 7a, and ending up with 8a. And then our B's are a little bit different. They do start with 3b, 4b, and then 5, 6, 7, all of this group is 8b, and then we have 1b and 2b. So this is another common way to number where you are. We do have 2 rows down here. They're actually cut out of the periodic table. If you look at the numbering system, you see that they fit down right here, that they've actually just cut out some of the periodic table. The periodic table should be twice as long as it is. But if you look at the numbering system, that will direct you to go down below. You do need to know the names of the families. So starting over on the left-hand side, this is the alkali metal family. So you should have a periodic table that you can look at. Go ahead and stop the video if you don't have your periodic table out in front of you. But you want to write the name of the family right above. So this is the alkali metal family. Now, hydrogen doesn't have a family. It's just tacked on there right above the alkali metal family, but hydrogen is not a metal. So hydrogen is just hydrogen. Doesn't have a family, doesn't really belong to any other element, but it is found right there over the alkali metal family. The next family is your alkaline earths. These right here in the middle, these are your transition metals. And then we have 4 families that they just start off with the first member of the family. So we have the boron family, the carbon family, the nitrogen family, the oxygen family. And then the second to last family, those are called the halogens. So you do need to know that family that starts with fluorine, they're called the halogen family. And then we have those noble gas family that William Ramsay discovered. The rare earth metals are down here below, and as I said before, they cut it out of the periodic table and they stuck it down here. The first row is called the lanthanides. Sometimes they're called lanthanoids, so you might sometimes see it written that way. I think lanthanide is more of a current name. And then we have the actinides, so the ones that are on the very, very bottom row. On the periodic table, there is a little stair-step pattern right here that goes down, and this separates the metals from the nonmetals. So metals over on this side, we have nonmetals on this side. Remember that hydrogen's kind of different and it's hanging out here with the metals, but it is a nonmetal. The ones that are this purple color, those are the metalloids, and there are 6 of them that you need to know. They all have 2 sides of their box will be on that stair-step line. So we have boron. Aluminum right here, it is a metal, so it is not a metalloid. It is so metallic that it's just considered a metal. But so even though it has 2 sides on that stair-step, it is a metal. So that's the one exception you do need to know. So boron has 2 sides on that line. Silicon does. Germanium, arsenic, antimony, and tellurium. Below that, there's some controversy on if these are metalloids or not. They're radioactive, and so nobody really wants to do research on just to find out if they're a metalloid or not. And there's some argument about them. So I will never ask you if those are metalloids or not, or if they're metals or nonmetals. Just know these 6 metalloids. A metalloid has properties of some metals and some nonmetals. I kind of call them the tweeners because they're right there in between the metals and the nonmetals. But you can see most of the periodic table, they are metals. Also on the periodic table, they do have a color code system to let you know what state of matter they are at 25 degrees Celsius. If they're a solid, they will be black, so have a black letter. Liquid would be blue, gases would be red, and if you ever see an outline like titanium, that means that it's man-made. It's not found naturally in nature. A lot of these actinides down here, these are man-made. We've done some atom smashing to be able to come up with some of these heavier elements, and especially the ones down here. Go ahead and stop the video and see if you can answer these questions. So classify as a metal, non-metal, or metalloid, and then name the family for each above. All right, we're back. Let's go through and classify each of these as a metal, non-metal, or metalloid. So aluminum, even though two sides are on that stair step, it is a metal. Sodium is on the left-hand side of the periodic table. It is also a metal. Oxygen is a non-metal. It's found on the right-hand side. Silicon is a metalloid. I'm just going to do a D for metalloid. Neon is a noble gas, so it is a non-metal. And uranium is at the bottom, that last row there, the actinide series there. It is also a metal. Name the family for each of these. So aluminum is in the boron family. We have sodium. This is an alkali metal. Oxygen is in the oxygen family. Silicon, a metalloid, and it is in the carbon family. Neon, as I said before, it's a noble gas. And uranium, this is just a name, it's named by the row, or it's an actinide.